So our next speaker has worked on designing and programming low-level system drivers and is currently a cybersecurity and full-stack engineer. In his talk today, he presents a self-powered sustained irrigation monitor system using Blue Wireless Note Card and Note Carrier, which charge the LiPo battery through wind, water, and solar power. Please welcome to the Hackaday Supercon stage, Dr. Irak Mayer.
All right, well, hi, thank you so much for coming. Thank you to Supercon to open the doors to people that is just new to the environment. This is my first presentation, as you will notice. A little bit nervous here, but it's very exciting to be with so many people sharing the same passion. As you can see, we can do the check ID all there. And I as a first-timer, I thought it was going to be a 10-minute presentation. It happens that it's a little bit longer than that. I hope I can extend it a little bit, but it might end up early, which is pretty good because it's actually before lunch, so everybody can actually go have lunch. How you? Oh, yeah. No. So what is the trouble that we're trying to address here? It's starting to become that now IoT devices are starting to be more popular inside our homes, which are providing electrical power directly from our system, from our electrical architecture inside our home. But what's happening with outside? That now that we want to expand that that usage of these devices outside and collect data. So placing the sensors devices in the wall and far away from our electrical infrastructure poses a challenge on trying to keep those batteries running on those devices without having to go every other day to refresh the batteries or change them. It usually are driven by LiPo batteries, and they need to be replaced periodically before they are depleted. What we are trying to create here is a place and forget approach. Devices that you just put out there in the wall and you just forget about them, but you keep getting data out of the systems. This study is basically based on, how do you go to the next slide? Oh, okay. It's actually based from my daughter, Elizabeth. She made a project over Hackster, a first attempt to solve the issue, and mostly because she was concerned about irrigation systems in agriculture. There is a lot of water lost and misuse because of lack of properly tracking down how much water and how much is being provided to the fields. So this actually is one of her slides during the sustainability summit at Hackster, and she was nice enough to share it with me. And basically it's mentioning about what type of irrigation systems are used out there in agriculture, although the results that I'm going to be showing, they can be applied for other fields, and I'm still stuck here with this. Okay, there we go. So what did we use for as the core system to try to track down this information? We basically used a Blues Wireless WiFi card, which is it's a new company that is providing a SOC system on a chip that can allow you to transmit data through cellular or also through Wi-Fi. In this case, we use their Wi-Fi card. We use their sorry about these pauses. It's just okay. There we go. That is the Note Carrier board that they have, and basically they have a M2C little chip board that gives you access to Wi-Fi or cellular, depending on what M2C board you are using. Not too fast. And then we use also an Adafruit ESP32 version 2 in order to collect the data. We are not using the Wi-Fi capabilities of the V2 because we are already using the Note card. capabilities. And then we also had INA 219 feather wind, that is a chip that allows you to monitor how much power you are getting out of the outsourced device. Like in this case, in the cases that we're going to be seeing is water turbines, solar panels, and wind turbines. So you connect the power that is generating that device into the INI 219, and it's going to give you how much current is coming from those devices, how much load is being taken out from the devices, and some other information. And then we also need a way to know how much power is being given to the LiPo battery. So we use an LC709203F monitor chip that what it does is keeping track if the battery is being recharged, how much battery left is in the LiPo battery. And finally, we use an OLED 1.5 inches to keep track of the information. Now, I kind of list all the elements here just so you can have an idea of how much power we are going to be driving out of the system, which if we put it out there, we are not going to need the OLED graphics display. We are not going to need the feather wind INI 219. So that's going to save power. So it's going to be running for a little bit longer than what we are currently using here. And let me see. So the whole system just looks like this. It's a little bit bulky, obviously, but it's just a prototype to try to figure out if it's going to work or not. So how does the whole thing work? So you have your data. I was hoping the screen was a little bit bigger, but hopefully you can see it. We have the devices that is collecting the data. Then it goes into the Adafruit feeder that is just working as a microcontroller to collect that data. Then the information is passed to the node card, which connects to nodehub.io, which is basically a temporary space where the data is located, and then from there you can reroute it to different cloud services like Adafruit.io or Amazon AWS or other devices, other cloud services. And in this case, we use Adafruit.io because it's, in my opinion, is the cheapest and the fastest one to use compared with the other ones that at some point your trial period ends and then you have to start paying. Let me see again. There we go. All right, so we started first with our water-based testing. We call it liquid electricity just to make a fun name out of it. We started it with just one water turbine that you can see it up there in the yellow. And then there is a water sensor that is nothing more than just a propeller that is counting how many revolutions the water is going through there. The turbine that we are using gives around 5 volts of power and about 93 milliamps of current. And as you can see here in the graphs, you have the current and then the revolutions per second. When the system is running, you obviously get a peak over there that gives you around 78 to 83-ish milliamps of power. However, it wasn't enough. As you can see on the middle one, the battery percentage starts going down as the system is used, and it goes all the way down to 0 and the system is depleted. So it was basically not helping at all with just one. And then I start thinking, okay, so how can I try to get more current out of the system? And we went into MOSFETs and superchargers, but it was kind of complicated to put them together. Well, not complicated, but didn't want to go into that direction. So then I started reading how batteries works together in parallel and serial. And there we go. And the funny thing is that parallel will give you, if you connect 2 batteries in parallel, it will increase the current, but it will keep your same voltage. If you connect them in series, it will increase the voltage, but it will keep the same current. So I thought, well, why I don't use that same principle with the water turbines? So I add another water turbine, and we have here, sorry about the sound, it's difficult to get used to this. So you have here the two turbines there, and then the water sensor connected to the same pipeline of water. And voila, I mean, I got a 5 volt out of it, constant voltage, but the current went up to 138 milliamps. But that, unfortunately, I thought I got it, and I hope that the video works. Is it working? Uh-oh. No. Well, that's an important part of the presentation. Okay, not sure why it's not working. Is there anybody that could help trying to figure out? Is it what? Is it on your desk? No, it's actually coming from YouTube. I did mention them. It might not work. Okay. Let me see if I can. Can I get access to a web browser? Click there. Okay, all right. All right. All right, thank you. Yay. All right. Launch slides again. Okay, so let's go to this one here. Right, okay, got it. Yay! Okay. Sorry about that, but that's what it goes. So, okay, the sound is not that it's not coming out, but basically you can see I turn off the battery, the LiPo battery, just to see if we had enough power to power the whole core system. And as you can see the little monitor, it kind of flashes, cycle powers. And that's because there was not enough current for the system to actually self-sustain itself when it was trying to connect to the access point through the Wi-Fi. When you get to the point that you run the Wi-Fi access point, it needs more current in order for it to, interesting. Yeah, I mean, I'm seeing there myself. Nice. Well, a lot of discoveries in this presentation, okay. I don't know how to turn off that, so let's just go to the next one. So looking into that issue, I thought, okay, so now, how can I get, there we go. Now, how can I increase even more the current? So what I thought, well, if 2 work for 153 milliamps, let's put 6. Let's try 6 water supplies. And here we see, you see a little, maybe you can hear it, but there is a little click, 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 click at the end because I added also a relay system in order to get the flow going every 15 minutes, every hour. So every 15 minutes, the system starts and works. And as you can see, I was able to get around 186 milliamps at that point. It actually goes all the way to 250, and you can see the system there with six water turbines running all together. One of the things that I noticed is that the flow sensor goes from 45 to 50 revolutions per second to 32. So actually putting that many water turbines, it actually affects the pressure of the water going out of the system, but it was able to get 153 milliamps. And if you can see here from the, from the graphs, you see the current peaking there every time the system was coming online, which is every hour. That's a 2 cycle in 2 hours, running 15 minutes. I'll explain the peak in a little bit, but basically when you hit the system running with a current of 4.5, 4.3, no, the current is, yeah, I'm not sure why they have 4 there. Anyway, it gives around 153 milliamps, and then you can see the battery, how it starts going up. So this is the battery percent. And I had it around at 5.5%, the battery percentage, and then during that period of time, in 15 minutes, it actually increases the battery percentage for around 1% of the battery, which is really good because it actually is recharging the battery. And then in the next 45 minutes where the system is not working, the LED screen and the communication with the node hub is still sending data. So you can see the battery going all the way almost to zero, and at some point it actually reaches zero. But even with a zero battery, when the system goes back online for 15 minutes, you start seeing how the battery starts getting charged again. And then yet again, it shuts down and it starts depleting again. And this is the revolutions per second here. A couple of disclaimers. There was an issue here with the counter that was taking measurements, so that's why you see it at 450. It's not that it went crazy and went to 450 revolutions per second, it's just that the program had a glitch there that I need to fix. And this other peak that you see there, I was just curious about what happens when you actually shut down the battery and turn it on again individually, so that's why you see a little peak there. So with these results, the thing was, okay, so what happens if I just don't want to use a LiPo battery? What if I just want to run the system without a LiPo battery? Will it work? And let's see if, now I have the same trouble again. Sorry about that. Per slide. Well, but we saw in two different slices with 2 turbine and the 6. So anyway, I'm just going to cut out and break it up here. The result is that, yes, it did. It actually worked. And you can see here in the picture, that little circle there, that's the LiPo battery connector. I just pulled it out, the LiPo battery connector, and leave it running with the turbine power. And as you can see from the graph, I mean, you have your revolutions, and then the battery is 0 because there is no battery connected. And then you can see in the current, it goes from 150, around 185 is actually when it starts doing the connection to the access point. And then from there, it kind of reduces because the connection is already established and it starts sending data to the cloud, to the node hub service. And for 15 minutes, I have only 12 points, but for 15 minutes, it actually runs and gives enough power to the system to power up itself and start running. So what it means here is that you can put this in an irrigation system out there and just forget about it. If the battery drains out, the only thing is that you're not going to have any data between the time that there is no irrigation running to the point that there is irrigation running, and then at that point, the system comes in and starts sending data to the, and it's also for knowing if there is any issues with the pipeline, because if there is no data coming in the period that is supposed to be running, then you know now that there must be some kind of leakage in the power. And actually, we are not kind of alone in this. This last month, the Oak Ridge National Laboratories, they published this research on trying to use the water pipelines in the US to generate power. Because it's basically a waste of energy that we are generating power to pump all that water through our pipelines, but we could actually recover some of that energy if we can harvest the kinetic power. So the other thing that it can be useful for, and I'm kind of working on it, is just imagine that you could generate a turbine that will give you around 500 milliamps with just one device connected, in this case, for a QT-Pi ESP32 Pico that is extremely small, and just connect these devices into your home system for water measurement. So you can actually figure out if you are taking too long in the shower, like my wife always tells me, or if you are actually saving enough water when you uses your water machine. So that would be something interesting. So if anybody here can figure out a way to generate one of those turbines that creates 500 milliamps, that would be great. I think my knowledge kind of stops there. but having a community here, that would be great to try if anybody can figure out. So that was the liquid part. So what about the solar part? This is going to be a little bit faster because there is not that moving parts. I actually use 4 solar panels that gives you 5 volts, and when there is a really nice sunny day, you can see how the battery starts increasing through a really nice couple of hours of solar power, and it actually allows you to recharge the battery and make the system self-sustained. So solar, as we all know, is a very known source of energy to recharge things. And then the last part is the electrical air or wind power. And for this, I used to, from Amazon, 2 turbines, 2 wind turbines, and connected to blowers for, let me see if it plays. All right. And connected to 2 bit pumped air turbines. And both of them, they actually give me around 70 milliamps having 2, which it wasn't enough to actually recharge the battery or run it. But there is some more studies with wind turbines like Oscar Garcia and Aliel for 3D printed vertical wind turbine that I think they are coming up with a version soon, which it would be allowed to give that much power. But as we are going to be seeing down in the conclusions, there is some withdrawals there. So the other thing I was thinking, and yeah, this one is not going to play either. So what happens if we try to use a standard DC blower connected to our cars? When we are driving, we are generating a lot of air friction through the car structure. So I kind of took that DC blower, and too bad that the video is not playing, but I was driving, taking the DC blower through the window and trying to figure out how much power would it get. I actually was able to get around 40 to 47 milliamps at 65 miles per hour, and that's with a little DC blower. So if you can imagine, if you put that thing on the top of your truck or the bottom of the car or on the sides of the doors, you could actually be harvesting that wind that is passing through your car structure, and I don't know, recharge something or connect it to a GPS system that could allow you to have independent battery tracking location. All right, so nice. So in conclusion, water flowing might not be a constant flow, but it's a scheduled flow. What does that mean? You cannot be pumping water 24/7 for an irrigation system because you would be killing the crops. But you can actually know exactly when you are going to be recharging the battery or when you are going to be getting data because it's a schedule point. Solar is weather dependent. If you have a very nice day with no clouds, then your system might be working pretty well and you might be getting data out of it, but it's extremely linked to how well your day is going to be, and if you can actually move the panels to follow the sun. And then wind is actually, in my opinion, kind of the weakest for having a very scheduled amount of data coming out from your system, because you cannot control the wind. You cannot know if you're going to have a wind enough day to generate that much data. I have to drive 65 miles per hour to get 40 milliamps. So that would be basically a hurricane kind of thing if we tried to put it over our homes. So as you can see, it depends on what kind of energy, but I do feel that harvesting that flow of water through the pipes, it's a good start to try to figure out things. So the QR code here is the Hackster page that I have with some other projects if you want to go and check. The liquid electricity is up and running. The solar and the wind, it's coming in the next week to be there. And I hope that you find this talk inspiring the way I found it when I was making the whole system, and that we can save at least 1 gallon of water from our irrigation systems. That would help a lot our planet at this point. So thank you very much, and if there is any questions, I'm here.